Hello, everyone. My name is Mustafa Hajij. I'm an assistant professor at Santa Clara University, and today I'm going to talk to you about topological deep learning. This is joint work with Kyle Esteban. So I will start motivating this work by talking about supervised machine learning problems in the statistical setting. In a statistical setting, you are usually given a dataset S that consists of pairs xi and yi, and this dataset is usually sampled from an unknown probability, joint probability distribution Pxy. And the problem is, after giving this data set, S, is to find the function f from the set x to the set y, such that f predicts the correct label y for a new point xy sampled from the same probability distribution P. For the purpose of this talk, we will only consider classification supervised machine learning problems. And in this case, usually the set Y is a finite set. And each Yi corresponds to a label associated with the point Xi. So an example that is usually considered is the MNIST dataset. So here each Xi corresponds to an image of a digit, and each yi corresponds to the label of that image. So in this case, so for instance, the dataset, the MNIST dataset consists of the following pairs. Each xi is an 8 by 8 image that represents one single digit, and each label is one hot encoder. It has 0 everywhere and 1 where that corresponds to the label. So here you have 6, and here it is in the 6th position. So we are seeking, in this case, a function from R64, so 8 by 8, 64, to R10. 10 here is the number of labels. So we are seeking a function that basically, after training, after seeing this data set, can predict the correct, what's the correct label on a given new image is sampled from the probability distribution that gives us this MNIST dataset. The way we usually find f is by defining some sort of cost function, c, that penalizes the deviation of the predicted labels fx of I from the true label y of I. So let's try to find a picture of what we are trying to do in a supervised machine learning problem. So I'm going to represent my space X by this manifold here, represented by the torus. And I'm going to represent the sample points that I sampled using my probability distribution P by those points indicated with the star points and with the circle points. And so you can visualize what we are trying to do is we're trying to find a mapping from this manifold to maybe a simpler manifold that basically separates those points that are the star points to one part of the manifold and the circle points to another part. So this picture motivates us to think about the input space and the output space as topological spaces. And we are acting on those topological spaces by a continuous function that deform the input space to the output space. So today I'm going to introduce to you topological deep learning. So topological deep learning is a formalism that is aimed at two goals. So the first goal is to introduce topological language to deep learning for the purpose of utilizing the minimal mathematical structure to formalize problems that arise usually in a generic deep learning problem. And the second goal is to augment, enhance, and create deep learning models utilizing tools that are available in topology. So of course, this is very broad, and I'm not going to cover everything about topological deep learning today. So for the purpose of this talk, I'm going to introduce things that are only maybe concerned with the first goal here. So I'm going to talk about classification problems from topological settings. So I'm going to define the classification problem using just topological tools. And in using this topological framework, I'm going to then show you when the classification problem is possible, when it is not possible. Then I'm going to show you the usefulness of putting things in this topological perspective. So I'm going to show you how very easily we can improve things that are not readily available using maybe statistical tools. So before we move further in our discussion, let's define neural networks precisely. So a network is a function from RD in to RD out that consists of a composition of other simpler functions called layer functions. So each layer function usually consists of a affine part. So you have a matrix W and you have a vector B. So that's the affine part. And also you have a nonlinear function, sigma. And this nonlinear function is applied coordinate-wise. So this affine function takes a vector and spits out another vector. So you apply this nonlinear function coordinate-wise to the output vector from the affine function. That's usually the layer function. So for the purpose of this talk, we will only consider a very simple nonlinear function called the ReLU nonlinear function. And ReLU of x is simply just max x and 0. So just if the number is negative, then it just returns 0. If the number is positive, it returns that number, basically. Sometimes those nonlinear functions are also called activation functions. So let's say that we have a classifier given in the form of a neural network, and we like to make a hypothesis on how this neural network acts as a classifier on the topological input space and deform it into the final space. So this is the image that we made earlier, a picture image on how a classifier might deform the input space into the final space. So remember that a neural network is a composition of continuous functions. So the hypothesis that we like to make and prove throughout this talk is that the neural network really acts on the input space by maybe massaging the manifold by those continuous functions, and at every step try maybe to deform the parts that are labeled by the star and the parts that are labeled by the circles, and try to separate them by acting on this manifold by those continuous operations. And hopefully in the final stage, it will arrive at this final shape where these two labels are separated in the final manifold. So now we're going to make the first experiment towards testing this hypothesis. So let's say that we train a neural network on the MNIST dataset. And after training, let's say that we look at the image of the MNIST dataset under this neural network. And we observe the final layer. So this picture here represents a projection for the final image of the MNIST dataset under a trained neural network. So you observe here that we have definite clusters. So you see a cluster for the 7, and a cluster for the 4, and a cluster for the 2s, and so on. And so you see there are a clear separation between various labeled parts of my data. And the question that we like to ask is how this happened. So we had the original data had some shape in its original embedding, and the neural network acted on it, and it deformed the original space into this final space. So we'd like to understand how this happens and why this happens from topological perspective. So let's start introducing the supervised machine learning problem from a topological point of view. So first, some notation. So I'm going to denote a manifold M of dimension n by M superscript n. And I'm going to denote by D to a disjoint union of manifolds with various dimensions. So the D here is a disjoint union of M1, I1, M2, I2, and so on, MK, IK. And I'm going to define the term topological data to be a continuous function from this set D to some ambient space E here, E, where E is usually some Euclidean space. So I'm going to call the pair DH by topological data, and E here would be called the ambient space. So this setting here clearly corresponds to the statistical setting. So if you take E here would be ambient space of the probability distribution that we introduced earlier, and that we sampled the data from, and the support of this probability distribution is the image of this function here h. So since we are going to talk about classification problems in this topological setting, then we also need to talk about labeling in this setting as well. So I'm gonna let a D and H be topological data just as before. And I'm gonna define, given D and H topological data, a labeling is just a finite set of subsets that are mutually disjoint and closed from H of D. So I'm gonna refer to D, the triplet D, H, and G by topologically labeled data. So note that the existence of the labeling is equivalent to finding a function from the union of these sets to a discrete sets that consist maybe of the indices from 1 to D. And you have, so this function basically determines this partition for the union of all those sets. So I will use either one of these definitions in the next slides. So now that we have the definition for topologically labeled data, we can start defining the topological classifier and start defining the topological classification problem. Let DHG be topologically labeled data. This is just as before. So you have a function from your original manifold, or maybe this union of manifolds, to the ambient space R of n. And G here is a function from DFL, which is just a union of the various labels. So this is just equivalent to what we had before. This represents this union of mutually closed, mutually disjoint and closed sets inside D. And a topological classifier is just a function from the ambient space of my data to some other space, R of K. So note that this definition here is consistent with what classifier is in a statistical sense. And we say that, so this is just a continuous function, so we did not do anything here. So we need to define what this classifier really successfully does something as far as machine learning is concerned. So we say that F separates the topologically labeled data if we can find D disjoint embedding k-dimensional disk. So this is k here is dimension of this ambient space, such that the image of each labeled subset of DL is contained in that disk. So note that here, D is the number of disjoint sets here. So D is the number of sets that are determined by this function G. So indeed, so topologically labeled a topological classifier, or even a classifier in a machine learning setting, try to separate your data. So if you are given maybe the data that's given by these two manifolds here, they are obviously, they cannot be separated within this ambient space, within the original space. However, you can imagine that you can maybe map this to a higher dimensional space and separate this data by disk that contain each one of them, and those disks are mutually disjoint. So from this perspective, a topological classifier take the data from its original space and maybe massage the manifold via a continuous map, or maybe a sequence of continuous maps, and separate those data. And our condition for separation is finding a mutually disjoint embedded disk inside the ambient space, where this is the codomain of the function f. So the first question that we like to ask is that, given a topologically labeled data, can we always find a continuous function that separates this data? So in order to show anything about this, we're gonna recall some classical facts from topology. So we're gonna first recall the Euruson lemma. So Euruson lemma states that if you are given a two disjoint closed subset of a normal topological space X, then we can always find a continuous function f from x to 0, 1, that sends the set A to 0 and sends the set B to 1. So just given this, this little fact, we can show that topologically labeled data are separable by continuous functions. So, so let's state the theorem. If we are given a topologically labeled data, so this is as usual, you are given a function h from a disunion of manifolds D to some ambient space RDN, and here I'm assuming my data is labeled by two labels, and we can extend this to n labels, and for the clarity of presentation, I'm just gonna state the result for two labels. Then we can always find a topological classifier that separates this data, and the proof is really easy. So by definition, this labeling function induces two closed and disjoint sets. So D1 and D2, these are just the inverse images of these singletons here. And by Euler's lemma, there exists a function from D to 0, 1 that sends the first set to 0 and the second set to 1. And since D is closed, being compact set of our Dn, then by also Euler's lemma, basically, we can find a continuous function from Rdn. We can extend this continuous function to the entire space. So I'm going to denote this function by f. And this f in particular coincide with the function f star on the set D. So in particular, this function sends D1 to 0 and D2 to 1. And so hence this function separates the data. And it's not difficult to extend this to find a function from Rdn to Rk for any k. So the separability on R actually guarantees the separability for any dimension k. And you can also extend this if you have n labels. And this is again an extension of Euler's lemma on n labels. So we have this lemma here, which can be proven by applying Euler's lemma multiple times, basically. So if you are given multiple closed and mutually disjoint sets, so n one of these, then there exists a continuous function f from x to r that maps each set ai to I for I equals to 0 to n. So far, we have studied the separability question in the context of continuous functions. So now we like to ask the same question in the context of neural network. So I'm going to let DHG be topologically labeled data, just as before. So I have a function h that map my disunion of manifolds to the ambient space Rdn. And I have a label function g. And we like to ask this question: can we always find a neural network defined on Rdn, the ambient space of my data, that separates the data DHG? So we start by framing the softmax classification neural network using topological terminology. So let me introduce what softmax classification neural networks are. So a softmax classification neural network is not very different from a ReLU neural network, except that it has a special function at the end called softmax activation function. And the softmax activation function is, I'm going to give you the exact definition in a little bit. It has a codomain, the n simplex. So I'm going to denote the n simplex as usual by delta n. It has n plus 1 vertices, just the standard n simplex, the convex hull obtained by those vertices. And the softmax function on n vertices is a function from Rn to the interior of the n minus 1 simplex, and it's given by composition of two simple functions. The first one is the exponential function. So you apply, given a vector on n coordinates, you apply the exponential function coordinate-wise on these coordinates. And the second one is a normalization function that takes a vector and then takes the summation of all those coordinates and then you divide by the summation. So a network net is called a softmax classification neural network with n labels if the finite layers if the final layer of that network is a softmax function. So n here will be always the number of labels in the classification problem, and each vertex vi corresponds precisely to one label li plus one in the label set that we introduced earlier. So this is just for the correspondence between the notations that we had earlier. So if you are given a data set that looks like this, it would let's say this is the annulus with maybe 3 labels, then what the neural network is trying to do, if you restrict its codomain to the simplex or with 3 vertices, and it's trying to map this region over here to this one, and this light blue region to this one, and this region here to this one. And so as far as the cross entropy loss function is concerned, the cross entropy penalizes the deviation of the mapping of all those points from this vertex, and it penalizes the deviation of the map of all those points inside this region to this vertex, and similarly for that vertex. So topologically, this mapping here happens through a sequence of continuous functions. So those sequence of continuous function must bend, quotient, and does all kind of topological operations. They allow topological operations via those continuous maps in order to achieve this task. So which is continuously moving this space into this space here. So to gain more intuition on the problem, let's consider an example. So here I'm considering the torus labeled by 3 labels. So I have a green label and I have a yellow label. And to make this problem more interesting, I'm separating the yellow parts by a purple strip. So let's consider the action of a neural network on this data set and see how this neural network acts on this space and deform it into the final classification form. So the neural network that's going to act on this space is going to be from R3 to R3. So this is the input and this is the output for my domain and my codomain. And if after classification, this neural network maps this space here to this shape over here. And the question is, how did that happen exactly? So I'm going to go over the details right now. So the neural network that I considered when I trained on this data set consists of 6 layer functions. So these layer functions are given, have this specific form. They are functions from R3 to R3, and they are, so each W here is just 3 by 3 matrix. And the activation functions are just the ReLU functions. So they are max, this number over here, and 0. So let's see the application of all those maps on the activations and see how the neural network deforms the space into the final space. So the first function, the first nonlinear function, actually projects this space into this form here. So it gets rid of the hole in the torus. And the second one, the nonlinear one, bends this space this way. So it starts to bend the place where there is a yellow part. And then the third part, for which is the linear part in F2, W2, it bends the space here a little bit, or shear it a little bit. Then the nonlinear part takes this portion here, the yellow portion, and start bending it so that it needs to quotient it later with this larger yellow part over here. So, and this is indeed start to happen inside the third layer function. So the yellow parts are getting closer to each other over here, and the manifold starts to take a 1D dimension. So as far as classification is concerned, you really don't need all those topological information. You don't need the hole here, you don't need the other hole. All those are redundant as far as the classification is concerned. So the neural network is deforming the space towards this goal, towards making the points that are yellow close to each other in one vertex, and points that are green close to each other in another vertex, and so on. So let's observe this. So here, the nonlinear part actually started gluing the yellow parts together. So here you observe that the yellow parts are extremely close to each other. They are almost very close to being identified, and the green part got separated here, and the purple part got separated over there. So I'm not going to show you the rest of the function, but it actually deforms. The deformation from something like this to the final shape is not very difficult. So we also run an experiment on the same data set that illustrate an interesting behavior also about neural networks. So I'm considering the exact same data set that I had earlier and an almost exact same neural network. So I have 6 layer functions, except F1 goes from R3 to R2, and F2 goes from R2 to R3. So if we observe here, the first projection actually is a bad projection as far as the classification is concerned. So the neural network quotients part of the manifold upon itself. So it quotients the wrong portion on themselves. So the here part of the green gets glued with parts of the yellow, and parts of the purple gets glued with part of the yellow. So it's a total mess. So if a topologist was given this task, it would not do this choice probably. It would make a choice like this one here. So the neural network is given the right amount of space, but yet nonetheless it made the wrong choice here. We're going to give some explanation at the end for why this behavior happens. And it has also shed some light on the interaction between neural networks and the underlying topological space. So let's consider this a little bit more precisely. So a point X in my topologically labeled data. So if X is in the domain of the neural network, and then the image of this X is going to be in the simplex D delta n minus 1. Here I'm assuming that I have n labels. Then by definition, X is assigned the label Li plus 1 if and only if the image of X belongs to the interior of the Voronoi cell associated with that vertex I. Okay, so this is just immediately by definition. So we immediately get the following theorem. Let's rephrase this in this topological language. So if DHG is topological labeled data, again with H, it maps D to script D, and which is contained in the ambient space RDN. And if DL is the labels, and then the softmax classification neural network separates the data if and only if the image of each label inside DL gets mapped into the interior of the Voronoi cell associated with the vertex VI. So this is just a restatement, a topological restatement of what's happening earlier. So this theorem here characterizes the separability of a topological data by a neural network, but it does not tell me exactly if a neural network is capable in the first place to separate a topologically labeled data. So we like that, of course, we like something like to always happen, just like in the case of continuous functions. So the separability theorem and another fact known in the literature of deep learning called universality of neural networks can actually be utilized towards this fact. So universality of neural networks essentially states that any continuous function can be effectively approximated by a neural network to an arbitrary precision. So if we combine the separability theorem that we had earlier and with the universality of neural networks, then we can always, given any topologically labeled data, we can always effectively separate it by a neural network. If you are given a topologically labeled data, then you can always find a neural network that separates this topologically labeled data. So I want to go the other way around here. And to show you that this interaction is non-trivial, So I'm going to state a theorem that seems obvious, but we think this theorem is generalizable for any neural network. We're going to talk about this a little bit at the end. I'm going to choose a neural network with a specific architecture. So I'm going to force the first function to go from n to k, where k is a dimension less than n. And let net1 be arbitrary. Okay, so I'll be only restricting the first function. Then what this theorem is claiming, there exists a topological labeled data with the appropriate dimensions. So the topological labeled data has an ambient space, the input space, and that is not separable by this neural network that I started with. So you can always construct something like the proof is really simple. You can pick a data set like this one. Let's say let's say the ambient space is 2 here. I'm proving it for 2. Then you can pick this data set like this one, and you can prove that this thing here starts with a linear function, and it has to basically to map this to R1 since k, or to R0 since k is less than 2 in this case. So it has to quotient the space into something that it's not going to be separable as far as as far as the separability that we defined. So the neural network with this architecture would not be able to separate this data. So since we are considering this example, let's actually consider a neural network that separates this data. I think this example has some insight on how neural network operates, so I will go over the details of it. So consider this is my topologically labeled data, and I'm considering a neural network that consists of 6 layers. So I'm going to show you the architecture for this neural network in detail. So the first layer that I chose goes from 2 to 5. So we're going to again talk about this at the end, why we chose 5. And so this I'm projecting here for visualization purposes the data set from R5 to R3. Using for the dimensionality reduction algorithm, I'm using isomap so that I preserve as much as possible of the local properties of my original manifold in R5. So you see here in the projected image, the neural network starts to bend the space. And this is actually what a topologist would do. It will take this cylinder basically and try to bend this towards the goal of later identifying the yellow parts together. So you see here in the case more clearly in the next function. So this is the linear function of f2. I'm taking that from 5 to 5 again and projecting using isomap. So you see here it bends more towards this cylindrical shape, and all those dimensionality right now are not needed. So this is again the same observation that we had earlier. So the neural network cushions out all the space into one-dimensional space, and now you're going to see that it's going to start to bend those yellow parts together. So this is if you consider the next non-linearity here. So you see it start to bend the space now towards the goal of maybe cushioning those yellow parts at the end. So you see here that it's not visible here in the picture, but actually parts of those got cushioned out here, and there's only this not very well classified portion, and the neural network in the next one takes this portion here, this small yellow portion, and stretch it out all over this part here, and then in the next one it just cushions out all those parts, and in the final softmax function stretches all these parts here towards the middle and stretches all these parts here towards this yellow region here. So all those yellow regions inside and outside gets mapped to here, and the purple strip gets mapped to over here. So far we have given characterization for separability. So this is the mapping from here to the final space. And what we also like to do as well is we like to understand or characterize what the neural network is doing as far as a sequence of topological spaces. So we want to understand exactly or characterize from topological perspective what the neural network is doing um, uh, as it's acting on the input space to define a topological space. So towards this goal, let net be a neural network that consists of L layers. And I'm going to define the ith head of this net to be, I'm going to denote that by net superscript of I, to be the composition of the first I function. And if I'm given my data set to be X, then I'm going to define X superscript of I to be the image of the ith head of the input topological space X. In the deep learning literature, those sets are called the activation of a neural network. So we'd like to understand the neural network net by understanding how the neural network acts on the input space X and how it deforms those sequences of topological spaces. So to achieve this goal, we're gonna try to understand how each individual building block acts on those input spaces. So these, in my case, I'm going to consider ReLU activation functions, and then we're going to try to understand how the neural network acts as a whole, as a continuous function, and how it's trying to accomplish the classification task. So let's consider the action of a ReLU activation function on a given set A in Rn. So if you are given a set A in Rn, then the ReLU activation function maps this set in Rn to another set. We call it the image, obviously, ReLU of A, in one of those three following ways. So let's consider the figure here. Then I'll explain how the correspondence between the figure and what we have over here. So if we have, suppose that you have this data set here. This is my A. So this my A here is in R2. So what the ReLU activation function is going to do here is going to leave all those points in the first quadrant without touching them. It's not going to move them. It's going to act on them by the identity, basically. However, the way it's going to act on this quadrant and this quadrant is going to quotient those by mapping all the points and project them on the y-axis here and projecting them on the x-axis, and it's going to quotient all the portion from the third quadrant. It's going to quotient all those points to one point, which is the identity. So as far as the definition is concerned, this just makes everything positive. So take all the points and you just make it. You just take max that point. Max that coordinates and 0. But as far as topology, if we think about this as a continuous function, this is a quotient map. It's quotienting all those parts to this portion, all those parts to this portion, and all those parts to this portion. So, however, the dataset A might not be always like this. So this is how it acts on the entire plane if A is R2. So if otherwise, let's say that my space looks like this, then ReLU is not a quotient function, or it does not strictly like glue parts of the space on itself. In this case, ReLU will act as a homeomorphism actually. So here you have this space, the input. This is my A, and the image of this will be just the same space topologically, just bent at two locations. So ReLU here bends actually the space. So the first case, we are quotienting some parts. So the quotient is determined by the so they are 2 points have are quotient if and only if they have the same ReLU. So this is the first part. The second part is actually the two spaces are homeomorphic. Just the ReLU function here just bends part of the space. And it can actually, if the third case is actually not mentioned here, if the space is entirely in the positive quadrant, then the ReLU activation function is just the identity. So this case here is actually an interesting case, which is a combination. It seems that this case here is this case, but it's not. So in this case, all the points in the third quadrant get mapped to the zero, and all this part here is projected on the x-axis, and all this part is projected on the y-axis. So this is a combination of the first two cases, the quotienting and the bending. So we saw the role of the ReLU activation function on the input space. The other role, which is the role of the matrix, this is well known and well understood. So matrix W acts on the space by rotation, scaling, translation, and sometimes it quotient also some part of the space. So these are the possible action for the matrix W on the input space. So if you put all of these together, then you can think about what the neural network is doing as a continuous function. So the neural network, what the neural network is doing, it's acting on the space by a finite sequence of topological operations. So these are translating, rotation, quotienting, and scaling, and bending. So in order to achieve, and the final goal for it is to achieve the classification task. So for the classification neural networks, the final desired map is to map all the labels into the corresponding vertices of the simplex. Then what the neural network is trying to do via those topological moves is to find the appropriate sequence of bending, scaling, translating, rotating, and quotienting to map the space with those allowed moves to the final space here. So let's state this precisely. A softmax classification neural network is trying to deform the input topological space to the simplex on n vertices, such that each subset with label I plus 1 is mapped entirely to the Voronoi cell, or the interior of the Voronoi cell associated with the vertex I. Okay, and the neural network is trying to do that via a finite sequence of continuous topological operations: bending, quotienting, rotation, translation, and scaling. So this is done by understanding what each layer function is doing, and by using this topological terminology as well. So given the above setting, we like to think of a neural network as a topologist that is trying to deform a space A to another space B by a finite sequence of topological operations. We saw that in the case of a ReLU neural network, those operations are bending, scaling, translating, rotating, and quotienting. And actually, it's not very hard to convince yourself that for any nonlinear function other than ReLU, this is also the case. And this analogy here is very closely related to the fact that the parameter landscape of a deep neural network has a very large local number of minima. So let me explain what I mean by this. If two topologists are given the task of deforming the input space here to the final output space, then very highly unlikely that these two topologists would agree on the sequence that they will use in order to achieve this classification task. So if I constrain those topologists by the spaces, just like I do for the neural network, then these two topologists would probably make different choices, say, for the first projection. And similarly for a neural network, if I train this neural network one more time, I will probably not going to obtain the same sequence, but I will probably achieve very good task at the end as far as classification is concerned. So this is consistent with this observation that has been proven over and over in practice, that local minima consistently provide similar level of performance on multiple experiments, and that are very close to the global minimum. So from this perspective, there is some sort of correspondence between local minima for the landscape of a deep net and distinct sequences of continuous operations that yield topologically equivalent sequence of spaces. So earlier in our experimentation, we made a choice to map topologically labeled data from its space to a larger space. And the reason for this is actually heuristic. We did not prove any result about this yet. So this is just an observation that we noticed why we trained those neural networks on manifold of dimension M. So we observed that if we put the manifold in its general position, then the training becomes much easier. The general position theorem asserts that any M manifold unknots and unlinks if you put it in high enough Euclidean space. So strictly speaking, a neural network really does not need this much space in order to separate the data. One form of the universality actually tells you that you only need to go one dimension higher than the ambient space. That's usually enough to approximate any function. However, in our experimentation, we noticed that we don't need to make the neural network as deep if we put the data set inside its general position dimension, so larger than 2m plus 2. So let's see and study an example that illustrates the relationship between knotting linking and neural networks. So here in this example, I'm considering a data set of two toruses that are linked together. And I'm acting on it by a neural network that consists of 6 layers. So I'm going to show you the action of this neural network after training on this data set. So the first function that I chose for this neural network, it actually maps the data from R3 to R7. And the reason for mapping things to R7 is again related to the general position theorem. So here I'm given the neural network a little bit extra room to manipulate the space to mapping things to not to R6 to R7. And you see here the data has been separated. Recall earlier that actually if you map things here from R3 to R3, the neural network will never be able to separate this data set, because at best we saw that the ReLU layer function acts on this data set by a homomorphism. And we know that you cannot separate a linked data by homomorphism from R3 to R3. So you have at least to go to R4. If we observe the second activation function, so here data is almost separated. Here it's very separated, even the activation got farther away from each other. The same thing if I consider the next map, the neural network is quotienting parts of the manifold. So here the yellow part has been quotient to almost a point, and the other part is still a torus. But this is not gonna be the case. Everything is gonna be quotient out to as small as possible space. Because it's not needed as far as classification is concerned. Again, this is a repetitive pattern in all this, our observation and all the entire talk here. Every time a neural network does not need certain information, it tries to get rid of that. So the dimensionality is not needed as far as the classification is concerned. So it gets rid of it every time it can do that. So here from R7 to R3, you see here these clearly you started to see the 1D thing happening, and the 1D for this one is going to occur in the next layer. So you see here maps all this part actually to almost a point, and maps the other part to this line. So I'm not showing the last two functions here because they basically just modify this part just very slightly. Thank you for listening.